Hello everyone, today in this video I'm going to talk about the autonomous driving car using machine learning on Gazebo and ROS. So previously then we already done the part 1, creating a digital twin of the robot and preparing the environment, which we were able to achieve that we able to launch the robot in the simulation, Gazebo, and we also add the lidar sensor plugin and return the lidar sensor data in a scan topic, and we're also able to integrate the joystick to control the robot. In the part 2 we going to implement the autonomous driving in Gazebo. So to drive the car in the autonomously in the Gazebo environment, there are a few steps. It's the same steps that we have done for the real robot in the real environment. The first step is to collect the data from the sensor using a ROS node, and then we will do a data cleansing using a Python and using our custom lidar visualiser. The next step is to do a feature selection, that is to reduce the number of the independent variables using the select k best from the scikit-learn library. How it works is that imagine that we have 360 data points in a lidar data frame, but not all the data frames are important. The reason behind is that since the robot car is moving forward, so all the data point that is ahead of the robot is more important. At the next step, we will do the feature engineering, that is to create a new data by data augmentation. This is done by the Python as a part of the Jupyter notebook. And the last step will be training the train the regression machine learning model. We could do the multi-target regression model, or we can just do the single target regression model with the turn and having the linear velocity as a constant. So this is a diagram showing the process for our autonomous driving in the Gazebo. The first step, as spoken before, is a data collection. The second step will be data cleaning, and the third step is the model training, and the last step we do a real-time inference, which involve a ROS node calling the pre-trained model and then make the predictions on the scan data. So let's first take a look at the data collections design here. So we will have a node in the middle here, and then this node will subscribe for the 3 topics. The first topic is the joy topic, and this is to for the node to listen for the joy topic and then interpret the joy message, and then we want to control the recording of the data, like start and stop the recording. So that is for the purpose of listen for the joy topic. Secondly, we listen for the scan topic. This is obviously the scan topic is the lidar data topic, so we need to subscribe to this topic to get the data. And the third topic the node need to subscribe to is the command velocity. In the command velocity, then there will be component for the linear velocity and also component for the angular velocity. So in the case that we want to implement the multi-target regression model, we have to append both the linear velocity and the angular velocity in the CSV file format. But since we are only doing the turn, so we only need to record the angular velocity as the last column in the CSV file. So and here is the design for the autonomous driving. So first of all, it will listen for the scan topic, and then it will load the model from a file which result from the training, and it will for every data frame we receive, there will be a callback from the autonomous driver node, and this callback will run the inference from the model, predict into the turn, and then the turn will be used to construct the command velocity as a twist message and send to this topic. And we're using a ROS2 control. In turn, it will control the joint of the wheels and make the robot move in Gazebo. So now let's take a look how we can do the data collections and data cleaning and model training. So for the data collections, then we going to launch a data collections launch file. Just we can do this by running the command. So here that is launch the Avis for us to see the perceptions of the robot, and it's showing here at the bottom is the lidar scan, and on the top here we also have the camera sensor. And the purpose that I include the camera sensor here is I found it easy to navigate using looking at the camera. And in here then we have the Gazebo environment. So let me put them side by side. Okay, now we can take our joystick and then control the robot, and we can start the recording by press the button number 1, and as you can see in the here in the background terminal that is saying that the recording has been started. And then now we can use the camera view here to drive the robot, or we can just look at the map on the Gazebo here. So I will start driving the robot, and at the same time then our program is recording the data. So usually then in my experience when I doing the training, then is take around 3 rounds, then we will have enough data for training. And this is because we also doing the data augmentation, so we have a lot of data for training. We don't have to run to drive the robot many rounds. So, after we get enough data, then we can press the same button again, button number 1, to stop the recording, and this recording will be saved into a folder, this folder. And I think the one that we just recorded is this one. And so we go back to the design here, then we will do the data cleansing using the data visualizer. And to start the visualizer, we can let me stop the Gazebo environment and the data collections first, and we can go to the folder. Let's go to the folder for the data visualizer, that is in okay. So the visualizer will be in this folder, and to run that visualizer, then we gonna run the command Python run visualizer. So this visualizer is the improved version from the last one that I created in the last video. If you watch it, then for the real robot, and I created a lidar visualizer, and this is just the improved version of that. With this version, then you can do a few things. The first thing is that is visualize the data, as you can see here on the main panel here. And next is can do the data cleansing. That is when you in the inspection mode, as you can see here at the bottom, inspect, and then you can press the spacebar to move the lidar data by frame. And let's say that if you're not happy with this turn, then you can make the change. Like this one is let's say make it 0.5 is a better turn, right? And yeah, you make the change, and then the change will be saved later after you happy with all the changes to your data. Then you save it. It's basically one of the way to clean the data and make the data quality better. And another function that can be done using this visualizer is that you can do the data augmentation. There are a few things you can do: creation, augmenting new data by like rotating the lidar data here, and another one, you can flip the data vertically or horizontally. And next thing, you also can duplicate the data. Why you need to duplicate the data is let's say that there's a frame if you think that is very important, then you can duplicate it so that when you change the model, the frame will take more width. All right, so that is the visualizer, and which will help you to have a clean data. And after you're happy with the data, then we are ready to move to the next step, which is the model training. And for the model training, then we're gonna use the same Python notebook file that we used previously, that and we can run the Jupyter lab. Okay, so the Jupyter lab is loaded on the browser, and we can go to the notebook and open the random forest regressor. So regressor, this regressor is will load the data from the data that we let's say that we already cleaned the data. Then this will be the cleaned data, and then it's just doing some inspection of the data. And this is for like further data processing by removing the zero value, INF value, the value that is not doesn't make sense. Then it's remove the data and impute the data by just you know that the imputation is by making the average distance of two adjacent values. This is the same thing that we did in the previous video. And we can continue and run all the cells for training, and until we get the result. And I already done this, and the result I got in this data cleansing, and it is with this new cleansed data from the simulation, then I get R square of 88%, which is a very good model. So we are ready for the next step. Okay, so the last step is gonna run the inference, that is to run the autonomous drive. And we can do that. Let's stop the Jupyter notebook for now, and we go back to the ROS workspace, and we run the autonomous driving. Okay, so it's launched several programs. We can ignore this diagnostics monitor for now. I built this one for when I developing, and it's for diagnostic purpose. As you can see, that as output the information here for monitoring, and it also have the real-time plot of the velocity, and for loading the model for me to compare the new model with the previous model. And this is just for like we can manually control the velocity, we know that we only right now we only change the model for the angular velocity. So we can make change to the linear velocities and see that which velocity will be best for each of the corner, right? So if you see the environment here, then at this location, then we can increase the speed, and at, around the corner here, especially here, we should reduce the speed, right? So we can do this from the this program for the purpose of if you want to correct the data for the um, multi like multi-target regressor, but for now then just ignore about this one. And here then we have the Gazebo environment, and the same thing, we also have the RVs here for the robot perception. And let's have our Gazebo world opened here, and take our joystick and to start the autonomous driving. Then there's two modes. One is for inspection, that is you run the robot movement every prediction step, and the second mode is that having the robot to move continuously. That means that the prediction is happen continuously, right? So you can see, since our model is 88% for the R square, the movement is very good. All right, so let me stop the simulation for now, and let's go into our source code and to see how it can be implemented. All right, so here is the source code repository. So let's first take a look at the data collections, and let's go back here to the design. So we have the lidar data collector, and this will it will subscribe to 3 topics here. So that should be happened at the init function here. So you can see that here's the scanned subscriber, and here's the joint subscription, and here's the command velocity subscription. So to record the scan, then we actually implement so-called the YAML file for the configuration, and the configuration will be loaded during the initialization of this class. So this is the YAML configuration for the data collector, and we have a few parameters here. The first parameter is for recording, so which button will be used to start and stop the recording. And then we have the frames ticker, that is the number of frames that we will append to the CSV file. So next we have some parameters related to the collision detections. So here the minimum obstacle distance is 0.2 meter, and the scanned like scan view field view for the object detection is 60 degrees in front of the robot. And we have the locations, the configuration for the saving the data file. And last, we have the number of data points in the lidar data frame. These are resolutions for the lidar, and if you recall from our previous section, previous video, in the video number 1, then we define the lidar plugin for the lidar sensor. Then we also define the sample, which is the resolutions, and this number have to match with the one that we have here. Okay, so let's go back to the node. So this lidar character node, then the data saving will be in the scan callback. For every time um, the command velocity callback, we will store the current velocity in a in a properties in a local variable of the instance, and then for the scan callback, we'll be actually saving the data into a CSV file format. So let's go to that scan callback here, and we will have a several check here, checking for the data collections. We also check for that it has the same number of data points, and then we actually doing the saving of the recording of the data frame here. All right, so it will store the data from the range, which is the scan topic, and then we will also storing the current angular velocity. Yeah, so that's it for the data collector, and we can go on to the next design for the autonomous driving, which is the node called autonomous driver. Okay, let me close this one. All right, so for the autonomous driver, and it only have one subscription for the scan topic. So it's here, one subscription for the scan topic, and the subscription for the join is for the purpose like I talked about earlier, that can run the robot in the inspection mode. That is for every predictions of the machine learning model, then is will move one step, or it can run continuously. That is the purpose of us listen for the join topic. And the model will be loaded using this private method load model, and this here just implementations of the function to load the model using the pickle that load the file. And after we load the model file, then for every scan, we don't want to make the predictions every scan. Why so? Because if you make the prediction every scan, then it's inefficient, and it's also cost the computations resource, which in the case for the real robot, and you don't want to do that because it could drain the battery faster. So and it's unnecessary, like I mentioned. It's inefficient to do the prediction every scan of the data. This very much depends on the rate of the sensor. So that is some point that you need to note of. So let's see how it's implemented in the predictions, and and then send the command velocity to the command val topic. All right, let's go to the top. All right, so here we have the scan callback. Before going into the detail of the scan callback, it's the same like the data collector node. We also have autonomous driver.yaml, which is the configurations for the driver node, and there are quite a few group of parameters here. The first group is this one is for the what is the location of the model that we need to load, and then the second group is that for the vehicle controls, like the limitations of the linear and the angular velocity, and then we have some parameters for the safety measures. This is very important when we transit from the simulation into the real environment. is because definitely in the real environment we need to have the safety in place, otherwise our car will collide in some obstacle, right? And the next group of parameters is about the lidar configurations, and again we have to mesh the resolutions that is expected lidar points here. And the next one is also very important, that is decisive features, and this is have to mesh with the feature selections result from our training model. All right. And the next setting will be on the communications setting. The next one is about diagnostic testing, and I think I want to mention about this is very important one under the communication setting, the prediction hold duration and prediction angular hold. What does it mean? Uh, it's related to concept I mentioned earlier about that we don't want to make the predictions every data frame that we receive from the sensor. This is inefficient, and I already talked about that earlier. So for we will run the inference only, and the inference will be hold for a period, and that is the purpose of this parameters. So it will work this way that after the predictions, we will keep this step for 0.07 seconds, and then it will allow the next prediction to occur, so we can tune the value for a smooth driving. I think when I demonstrated earlier, you can see that the robot cars is driving around the maze in very smooth way. So we can use we use these two parameters to tune that the robot is smoothly driving in the maze. And this second parameter predictions angular hold, which means is that after the robot make the movement, the turn, then it will hold that velocity, angular velocity for this amount of time, and then it will go straight. Um, yeah, so that is how it works. You can imagine that we don't want to you turn the robot, and then you don't want to keep turning for the whole time of the prediction whole period. You don't want to do that. You only want to make the turn for some period, and then you go straight, and this is for that purpose. And I found that by implement this, then the robot movement is very very smooth in the Gazebo environment. I haven't tested with the real robot yet, but very soon I will do that in the real environment. So now let's go back to the autonomous driver, and we will have the message for the scan, and then let's see the implementation detail, and it's just some implementation for the emergency, and the one that I was talking about, the two parameters. This is exactly where it implemented. So the holding should predict the timing, so we don't predict every data frame received from the lidar sensor. And the conditions will indicate that when we should make the new predictions. So yeah, so this is we make the after we make the predictions, you can see here that predict the angular velocity from the lidar range, and after it make the predictions, it will construct the command velocity by, and then publishing its command to the CMD val, and and then the robot will be moving in the Gazebo environment. So that is how we implement the autonomous driving in the Gazebo environment. Um, yeah, and probably I will publish the code, but you give it a try, and if you have any like issues or on the way, then I'm happy to discuss. Leave a comment below. Thank you.